Hey everyone, welcome to another Chainlink workshop. We are going to just wait for a couple of more moments for everyone to jump in, and then we can start. So I will be monitoring this live chat on YouTube, so feel free to post comments, questions, whatever, during the workshop. But obviously at the end we will have a little Q&A session. So I will try my best to answer all the potential questions you guys may have. Okay, let's officially start. I think we're good. So welcome again. I hope everyone is having fun, enjoying this hackathon. I hope you guys build some amazing stuff. Really looking forward to this. And today's workshop is about knowing and controlling your smart contract address with EVM Opcodes. It's basically, I will explain to you how EVM handles smart contract deployment, which opcodes is EVM using for that, and also we will try and see the way how to know your smart contract address even before deployment to whatever chain. So it's like really awesome and powerful feature. My name is Andrej Rakic. I'm a blockchain developer and a new developer advocate at Chainlink Labs. On this slide, you can see my Twitter and LinkedIn handles, so feel free to reach me out after this workshop if you have any questions, comments, whatever. So let's start with the agenda. First, we're going to cover what EVM is and how it works exactly. Then I will explain to you what Create2 opcode is and how you can use this opcode to pre-compute your smart contract addresses even before deployment to the actual blockchain. And finally, we will have a little Q&A session at the end where you can just ask me whatever you want. So I will just paste you the link to this GitHub repo, where are all the code for this from this workshop, and then you will just can follow along basically. Okay. So this is the repo. GitHub Andrej-Rakic-create2. So feel free to clone this repo locally, and you can just follow everything that I'm going to do during this workshop. Okay, let's start. So what is EVM? The EVM stands for Ethereum Virtual Machine, and it's a computation engine that handles smart contract deployments and execution. It's a part of all EVM-based general-purpose blockchains. Because of this thing, EVM, we have so many general-purpose blockchains. For example, you have a Bitcoin blockchain, and with Bitcoin, you can only transfer money. You can only transfer Bitcoins. It's just a blockchain for money transfer. You can execute some simple scripts, but that's it. With EVM and EVM-based blockchains, you can have, as I said, like general purpose programs. You can code DeFi apps. You can code DAOs. You can code whatever you want because of this thing called EVM or Ethereum Virtual Machine. So what is this EVM exactly? We have Solidity or Viper. That's the languages for writing smart contracts for general purpose blockchains. So let's say, for example, we are coding a Solidity smart contract, contract.sol, and we have that one Solidity file. When we want to compile that one Solidity file, it needs to go through Sol's compiler, Solidity compiler. And there's like a different versions. 0.8 is like the latest, whatever. When Solidity file goes through Solidity compiler, as the output, we have at least two files. One is contract.abi, and the second one is contract.bin. So about the ABI, I think like all of you already know what ABI is. ABI stands for Application Binary Interface, and it is a simple JSON. It is a standard way to interact with contract, both from like outside world, like from our front end, for example, both for like contract to contract interaction. When you basically you can call function on another contract from your contract. That's all because of the ABI. Our focus today during this workshop is this another file, contract.bin. This binary file has all the instructions and like language for programming EVM. In this binary file, you have all the necessary inputs for EVM, and EVM knows how to handle all of these instructions coming from the Solidity file. So what is EVM? EVM is stack-based machine which use last in, first out stack to hold temporary values. So what's this last in, first out stacks mean? It means that if you push 3 values to the stack, let's say 1, 2, 3, it will be push 1, push 2, push 3. And then when you want to execute the pop function, pop, now the 3 is out of the stack. The 3 is being kicked out of the stack because it's the last in element that is being pushed to the stack. And last in, first out, you have like the 3 is kicked out of the stack. EVM has no registers. There is only that thing called stack, and that's it. Stack memory you will see later, but there's no in-memory register. For example, at CLang, at that assembly view, you have AX, AH, for example. Here, this is not the case. There is no register. And EVM also has its own language called EVM Bytecode. And this EVM bytecode is stored in that .bin file. Okay, so let's start with a simple example about what is bytecode. So this is a bytecode view of some small set of instructions. So it's not like really readable at first glance. You see like 60056004001. Like what's that all about? But if you go to this link, it's ethervm.io. This is the Ethereum virtual machine opcode summary. You have here like the table with all of Ethereum opcodes. So you program your EVM stack machine by opcodes. Opcodes are those instructions for the stack. And you saw here like there's a 60 is the first like number. And if we go here in this table and click 60, we see here that the 60 stands for push 1 opcode. So push 1 means that this opcode will going to push one unsigned integer 8 value to the stack. So push 32, for example, is for unsigned integer 256, but for like the lowest one, unsigned integer 8, we will use push 1 or 60. So if we go back to our bytecode view, like push 1, 5, we are going to push number 5 to the stack. Then we have again push 1, 4. Now we are going to push 4 to the stack. And lastly, we have this 1. So what is 1? If we go back to our Ethereum virtual machine opcodes table, 1 stands for add opcode. And as you can see, this add opcode works like this. You have 2 elements on your stack. It's going to pop 2 elements, add them, and that summary will push back to the stack. In our case, 5 plus 4 equals 9, so it is going to push 9 back to the stack. If we go back to the presentation, here's like the assembly view of this bytecode view. As I said, push 1, 5, push 1, 4, and then add. This is just 3 simple opcodes for something to EVM handle for us. Here's the slides. This is our imaginary stack. It's empty now, and first opcode comes here in first instruction for the EVM to handle, push 5. Now 5 is on the stack. Stack is now has only one element, 5. The next opcode instruction, push 4. Now there's 2 elements on the stack, 5 and 4. Like 5 is bottom and 4 is at the top. If we do a little, for example, pop, 4 will be kicked out of the stack. But for now, we have 5 and 4, like you can see on this slide. The third instruction is add. And as I said, add opcode works like this. It pops 2 elements from the stack, whatever those elements is, and add them, like in some temporary memory, and that summary push back on the stack. So add will pop 4 out of stack, pop 5 out of stack, add them together, and their summary, 9, push back to stack. And this is the end of our execution. We now have number 9 on our EVM stack. Okay, so EVM can access and store information in 6 places. So these 6 places are stack, memory, account storage, call data, code, and logs. I bolded this memory and account storage because this is really important for you when you write your Solidity code, but I will cover all of these 6 places. So stack, we already saw what stack is. So it's basically a place where EVM opcodes pop information and push back onto the stack. Memory is a temporary place for storing some data. So this is information. So in memory, you store information accessible for the duration of a transaction. So you have one transaction, it has some steps, some opcode instructions, and the memory is accessible only during the duration of that particular transaction. So it's temporary. Account storage, so it's a storage of a smart contract. So we have like 2 types of account on Ethereum: externally owned accounts, EOA. This is basically wallets, your personal wallets for signing transaction, for holding tokens, etc. And the second type of accounts are smart contract. And accounts can have storage. And for smart contract, it is really important to have its own storage, because in that storage, you can store your global variables, for example. Call data. Call data is the data field of the transactions. And EVM can also access them. So if I go back to this simple transaction, it's on Rinkebuy, and it's from our previous workshop about full stack NFT Dungeons and Dragons app. So this is the smart contract for Dungeons and Dragons. It's a minting functionality. Here on Etherscan, you can see this input data, and it's like function request random character. We can decode that input data. It's ELF, you see. EVM is seeing like this, like a set of hex number, but EVM can access this data, and that's like this call data. Code is basically a source code of smart contract, and logs are everything that you emit via events. So when you write Solidity code, you have some events and you emit them, and it's kind of like logger, and you can EVM can access those messages, addresses, UINs, whatever you emit as an event. So this is the full schema of EVM, how it looks. And it's important for you to know that EVM is quasi-Turing complete. It's not Turing complete, it's quasi. Why quasi? Because all execution processes are limited to a finite number of computational steps by the amount of gas available for any given smart contract execution. So in theory, EVM is Turing complete. You can do whatever computation you want, but in reality is limited due to gas. So each transaction has this slot called gas available. So you probably know that you need to pay for these gas executions, and that's the reason why loops are anti-pattern in Solidity. All why we try to optimize our codes to spend less gas, to have less opcode instructions because of this gas available parameter. Because in theory, if we run out of gas, the execution halts. It's a 0-0 opcode, and our transaction is being reverted. So we have like program counter, which is just increments for like from one instruction to another. We have EVM code. It's from that, if you remember, contract.bin file, and it's being transferred to a set of operations. So operations can be push, pop, add, store, store, mstore, sload, mload, whatever. And these operations access like some of the parts of EVM. So this is the stack. We explained what stack is, how stack works. This is memory. If you remember, memory is here for storing temporary values only during the execution of transaction. This is the storage, and it's related to a smart contract. So it's not part of EVM, it's part of each account. EVM just can access them. So writing and reading from storage is really expensive, are really expensive operations in terms of gas. So be careful with this. And also, if we have message call basically means that our smart contract are going to call the function on another smart contracts. This also consumes more gas. And with message call, it's really important for you to understand that it's still a part of the parent transaction. So if we have some transaction which needs some opcodes to be executed on our smart contract, and we execute, program counters increments, gas available decrease, and at some point, at some line, we need to call another contract's function as a message call. It's not a new transaction, it's a part of the parent transaction. And now on the second smart contract, you have some set of instructions to be executed, and all of these executions are consumed by this gas available of parent transactions. So be careful with this to not have like transaction reverted situation because of too many operations. As I said, there's like memory versus storage debate, and memory is temporary while storage is persistent. And reading from memory, you use mload opcode for that. For writing, you use mstore opcode for that. For reading and writing from storage and do storage, you use sload and store. And sload and store are really, really expensive operations. So you need to be really careful with that. And for you, I have amazing video about just that topic. So during Smart Contract Summit, Alex Ron, one of the engineers from Chainlink Labs, hosted a workshop about his guide to the EVM, where he explained basically this, how to handle sload, store, how to write to storage, read from storage, how when he writes smart contracts, when he has like a storage variable in smart contract, always has a prefix s underscore to know that this is like expensive to modify, etc., etc. So I highly recommend to watch this video. It's on Chainlink official YouTube channel. It lasts only 20 minutes, so like it's really easy for you guys to watch it, to be fully concentrated while watching this video. It has a lot of useful information about this topic, so I highly recommend to watch this video. It's on Chainlink official YouTube channel. Okay, so let's start with now explaining create to opcodes. So this is the opcodes for deployment of the smart contracts. Typically, smart contract deployment is handled by create opcode. So either like from Remix or from Hardhat or from Brownie or earlier from Truffle, you have like some ways to deploy your contract via different like Python or JavaScript scripts, or with Remix idea, you just need to click on some buttons and that's it. But in the background, everything is handled by this opcode, so create opcode. You can see on the picture on the right, this is the schema of the transaction for creation, new smart contract just for deployment. So you have nonce. It's a number only once parameter. It's like whatever number can be. It's related to your wallet, externally owned account. So like on each transaction, the numbers gets increment, and that's it. Like that's most important. We have gas price and gas limit. Also, like that can be set manually via our wallet. You know how to handle this, like pretty basic stuff. VRF are just the parameters for signing transactions. Also, standard stuff that's important, but these three fields are just really important and different than like when you call a smart contract, when you send some tokens to another external account, when you send Ether or any other native coin for like Polygon, it will be Matic, whatever. It's different. So here, this two field is like the destination address, and it's empty because we are not sending money, we are not sending coins, we are not sending tokens, we deploy new smart contracts. So this is empty. Value is usually 0, except you have a payable constructor, and you need to specifically use message.value inside your constructor. In that case, this value won't be 0, it will be whatever number is. And data, in data field, you saw it like on the Etherscan previously during this workshop, it's the init code for smart contract deployment. And how is contract address is computed? It's a catch of sender address and nonce, and that's it. Like catch is a standard hash function in Ethereum. It takes sender address and nonce, whatever nonce this is, combines them, hash them, and you have like your smart contract address. Pro tip for you guys: if you want to make your front-end team's life easier, and you deploy your smart contract to several testnets and mainnet, you're doing multi-chain, whatever, usually you need to handle like different smart contract addresses. But if you create a fresh new account and as a first transaction deploy to all of these chains, you will have the exact same address on each of these testnets, mainnets, whatever. So this is like a really cool feature for you guys to make life of your smart contract team easier, front-end team easier. So what about Create2? Create2 was included during Konstantinopoulos fork, and it's a way to pre-compute address of a smart contract before deployment. So with this opcode, you will already know the smart contract address even before you actually deploy it to the actual blockchain. And also, like there's like one parameter that can be changed, so you actually can loop through all of possibilities to find like the special address for your smart contract if you want. That's really up to you. So how contract address is being computed using Create2 opcode? So if we remember Create opcode, it's a catch 256 of sender address and nonce, but with Create2, it's a catch 256 of 4 parameters. First is FF, and that's a constant just to prevent collisions with the Create opcode. Then we have the sender address as the same like as with Create opcode. Then we have the salt, and this salt is an arbitrary value provided by the sender, and you can change that salt to basically find your special smart contract address. And finally, to be deployed by contracts bytecode, this is the 4th parameter to be hashed during to be catch 256 hashed, and this is how we are going to have our unique smart contract address. So this is like the theory. Let's now start building this. I'm going to use OpenZeppelin's create to smart contract. This is just not smart contract, this is library. And we are going to create a simple hard hat project. So if I go to my integrated terminal, I'm on desktop, I will create a new folder called create2, and I will cd to that create2 folder. It's empty, that's all good. I will just add npx hard hat init command. And now we are going to wait to create a new hard hat project. We're going to create a basic samples project in this folder, git ignore. We're going to install everything, and that's it. Okay, so just for the questions, found it. Yeah, you have the link to the video. Okay. With create2, there's nothing stopping from returning to deploy to the same address twice. That's actually a good comment. And if you wait till the end of this workshop, I will have a little trivia question for you guys, similar to this one. So maybe you can then just join the discussion and see just what community thinks about that. So this is a really good question. What is the benefit of knowing your contract address ahead of time? Well, basically, Uniswap use that because they pre-compute the addresses of their pairs, pools, even before like actual deployment to the blockchain, because they have some mapping inside their factory to handle and hold all this data, and they just need to have the liquidity from both sides to deploy the smart contract, etc. You can also have some maybe platform where you create a new wallets for new users, but you activate their accounts only when they deposit funds to that wallets, for example, and you'll just handle this as a smart contract, not wallets. For example, just be creative. Is that 10 PM in it? Basically, yeah. Hardhat is a framework like Brown. Yeah, Hardhat is a framework where you write scripts and test in JavaScript or TypeScript. With Brown, it's the same thing, but you write scripts and test in Python. Okay, so as I said, we are going to use OpenZeppelin contracts. So I need to install this package also. So npm install OpenZeppelin contracts. Just wait a little bit more. Okay. Cool. I think we are good. Right now, I will open Visual Studio Code because this is my code editor. With code dot, I open the Visual Studio Code in the folder where I am now. So if I click Enter, we are now inside our create2 project, hardhat project. Okay, so it's simple. I hope you guys can see this. I zoom it as much as I can as possible. So this is this standard greeter.sol smart contract, some sample script, some sample tests, hardhat config. It's 0.084, so this is good. And yeah, that's it. So we are going to create a new smart contract, new solid file called deployer.sol, for example. And yeah, so we need just let's click the X license stuff. License identifier. Oh, I just can't lock it. Fire, and it's going to be MIT, for example. We don't care. Pragma solidity version will be 0.8. And yeah, so contract deployer. This is our smart contract for like factory contract for deployment and new smart contracts using Create2 opcode. We are going to deploy this greeter.sol smart contract. So as I said, we need this library from OpenZeppelin. I will import it here, and I will do something like this to save us memory. So create. Also, we need from our reader folder. Okay, so it's here. Reader, not folder, but file reader.sol. We need reader contract. Okay. We are good. Okay. So let's start with deployment. So with coding. So we need first a function to compute address. So we'll call function compute address. And if we remember the create2, the only non-constant variable is that salt, is the arbitrary value provided by sender. So we can just provide that salt with bytes32, and this will be public view function, which returns address, some new pre-computed address. And here, how to do this. So if we go back to the documentation, you can see here that this library has these compute address functions, which takes salt and bytecode hash as the parameters. So salt, we already know what is this. So what is bytecode hash? Bytecode from a contract can be obtained from Solidity with this line. So this is the creation code of our smart contracts. So we need something like this: return create dot compute address. Salt we already have. We need bytecode hash. So bytecode hash will be bytes memory bytecode hash, and as we saw in the documentation, this is type of reader dot creation code. And the last thing is that we need to hash this value. So this is catch256 of bytecode hash. And boom, this is our function from computing address. If we run now our integrated terminal, npx hard hats compile should be compiled successfully. Okay, nice. Okay, I need capital L here. Sorry, I will just close this. Okay, the second function that we need, because when we compute our address, we just need to deploy a smart contract. So that will be a function for deployment of smart contract. We can call it like function deploy greeter, for example. And that function also needs to have this salt parameter. So bytes32 salt, also public. This is payable. And returns reader address. Return it like this. So this, actually, this is type address. Sorry, I hope you can see this. Okay, address greeter address. So greeter address is like our return parameter is create2 deploy. And okay, let's see what this deploy takes as a parameter. So amount, salt, bytecode. Basically, we saw I explained to you how create2 needs 4 parameters for deployment. And with create, there's only address of a sender and nonce. Here we have constant, we have address, we have salt, and we have to be deployed contracts, so 4 things. Okay, nope. Yeah, here it is. So create2 deploy 0 salt And the third thing is, let's go back to the documentation. So amount 0, as I said during the slides, these values on, like, in most cases 0, because like a greeter constructor is not payable, is not using message.value. Salt is like a provided parameter, and bytecode, we are going to grab bytecode like this. Bytecode, it's pretty much the same as here. It's a creation code of greeter, so byte memory, bytecode hash. Okay, it's not hash, but this is hash. Okay, we can call it bytecode. And this is with this this deploy function returns a new pre-computed address, and this is like our return parameter. And boom, that's it. Like, we deployed our create2 smart contract with just this one line. The last thing is that we can emit some event. So this event can be deployed, for example. So this is just for the logs. Deployed. And let's see. Okay, address is okay to emit. So this is contract address, let's say. And what can we emit more? Well, let's do the salt. So salt is necessary, like that, to know why this address is just this. It's because of the salt. So emit deployed. Contract address is this greeter address, and salt is salt. Okay, that's pretty much it. This is our whole smart contract. I will just zoom out a little bit to see it. Just this, I don't know, 28 lines of code is enough for deploying a new smart contract using create2. So, okay, once again, in my integrated terminal, npx hard hat compile to see that everything's okay. Boom, everything's okay. So this is really nice. I just okay. Just I need to do it one more time because I don't like this warning. Okay, cool. Then the next thing, Ether.js has a really nice function called getCreate2Address. And this JavaScript function can also compute smart contract address for you using create opcode even before deployment. So my intention is now to try this function or method from ethers.js to see how this function computes our address, to see how our smart contract deployer pre-computes our address, and to hopefully make it like equal. So sample test.js, I don't think we need all of this, so I can just delete everything. I think that's okay. Okay, so we will start with a little before each hook. So before that, we need a deployer instance. So this is our smart contract. Before each, now this just before each. Okay, this is going to be async function because we need to deploy smart contract locally on local hard hat network. So constant deployer factory will be await ethers dot get contract factory of deployer. Okay, then next thing, this deployer is equal await deployer factory dot deploy, and then we need to await deployer to be deployed. So all of this sample code you can also find on Hardhat official documentation, like first thing when you write tests is this. So this is test in JavaScript. I usually prefer TypeScript in like production code, but for this simple demo, it's really okay to do this JavaScript stuff. Okay, so we're going to write only one test, and greeter should, we'll do not capital like this, should have the same pre-computed addresses. Pre-computed addresses. Okay, this is also an async function. Okay, so we need salt. So salt can be whatever value we want. We can have it like, okay, 18 number, for example. So check 256 of 18. So this is 18 in hexadecimal value. So this in hexa equals 18 in decimal. We need to provide a hexa value to catch 256. Okay, so this is our salt. It can be like whatever value we want. It's just random. We can just play with this value later. So right now I want to pre-compute smart contract address using deployer smart contract. So how to do that? Well, we have this compute address function. So we are just going to call that function. Okay, so const solidity pre-computed equals await deployer dot compute address function and salt. Okay, right now I'll just console log this solidity pre-computed and see what is going to happen. So npx hard hat test. Okay, so this is our pre-computed smart contract address of greeter to be deployed smart contract. And you can see like it's a regular smart contract address, 20 characters, perfect. I will just put this here. Okay, second thing, as I said, I want to now pre-compute this address using meters get create to function, get create to address. So how to do that? We need to pre-compute address using meters.js library. Okay, we need init code hash. But first, let's do something like this. So code const meters pre-computed can be get create to address to see what are the parameters. So we need like from address, we need salt, and we need this init code hash. So from is from our deployer smart contract, so deployer.address. Salt is salt, like the same, and we need this init code hash. So init code hash is a catch-up of bytecode. So bytecode, we can import it like this. So from let's find out our require. My mistake. Let's see. Maybe like this. Okay, it's in artifacts folder. It's in contracts. It's in greeter.salt. So we need bytecode of to be deployed smart contract and greeter.json. So this is bytecode. Boom, there it is. So catch-up of bytecode, and then we are going to provide this init code hash. And last thing, I'll just console log this ethers pre-computed address. And let's run our test once again. npx hardhat test. Boom, we have two addresses console logged, and they're exactly the same. So our smart contract is doing really well. Ether.js library computed in the same way, and just we need to make this a successful test. So unit test is not console logging. With unit test, you need to just have some expect syntax. So last thing, we're going to write something like that. So expect Solidity precomputed address to equal Ether's precomputed address. And that's it. And just now, one more time, npx hard hat test to see. Boom, our smart contract is okay. Our unit tests are all passing. Just one unit test is passing, and we are good. Okay, so back to the questions, because my mic is going away. Because we have a little Q&A session. But before that, I have, like, as I mentioned, a little trivia for you. So follow Andre_dev on Twitter and join the discussion. So what's the discussion? I will go here. So you need to follow this Twitter account. Here I will post something for you. So this is a tweet. Dear Web3 builders, here's an EVM trivia for you. How to change smart contract source code without changing its address. So I will just tweet this, and you follow me, go to this tweet and join the discussion. I will join this discussion later and see who gets this first. Okay, but before that, let's go back to our Q&A session. So let's see. This is great tip for someone who's thinking of multi-chain deployment. Exactly. I already said, like, if you have not create two, but regular create, and you want to do a deployment to multi-chains, just create a new wallet, fund it with some coins, and then do the deployment to each of these chains, like as your first transaction. And because create opcodes takes address of the sender and nonce, and these nonce will be the same because it's a freshly new generated account, you will have exactly same smart contract address on all of these different chains. So it's really nice for, like, your smart for your front-end team to handle these smart contract addresses. What else? Okay, I already covered this. Is there a chance? No. Is there a chance of collision with an existing contract when you compute a new contract address? No, because with create2, first parameter of that for is ff, and that's a constant to prevent collisions with create. About create2 with the same addresses, that's the question for you on Twitter. So join the discussion if you want answer on that question. I will also post it somewhere on Discord or Twitter or whatever. So just wait a couple of more hours and you will see. Okay, error trying to use. Okay, so error HH12, you need to install Hardhat on your machine to actually Hardhat init this project, but also you can git clone it from here. So this is the whole working example under Rakic create2 repo. So just clone it, and you have here a package.json, install it, and you're good to go. It has all the scripts. It also has some bonus contracts and some script to find the special address one for you. Okay, warning comes from extra n. Oh, extra n. Thanks. I didn't notice. I just this SBDX warning is really, like, I don't know. I'm just not going to say my opinion about that. Okay, awesome stuff. Let's go. This is Twitter. That's it. So, okay, guys, this is all of your questions. Thank you again for, like, having me. Thank you for attending this workshop. I hope you find it interesting. I hope you learned something new. I wish you best of luck by the end of hackathon. I really hope that you're going to build some awesome stuff. and see you around. Bye bye.